Good afternoon, everyone. My name is Alejandra. I work as a product engineer at Gasmet Technologies. I think this presentation was misplaced because it's about carbon capture. In the CCS, it's a bit different than CCR, so my apologies for not being too relevant to your interest, if that's the case. I wanted to talk about multi-gas FTIR monitoring and carbon capture. So FTIR stands for Fourier Transform Infrared Spectroscopy. My work at Gasmet has been in supporting field and stationary applications for FTIR analysis, with a focus on climate change research and other niche applications for multi-gas analysis. One of those applications is exchanges between soil and the atmosphere, especially of interest to soil scientists and ecologists trying to understand if their system is a source or a sink or of carbon and nitrogen. And if they're a source, then what's the footprint of those systems? So they need to measure the fluxes from soil. In the agenda for today, it's presenting FTIR as an analytical technology in carbon capture for presenting as well sampling configurations, its challenges, and case studies that go from research to pilot plant to commercial plants. It is known that carbon capture in storage allows for safe, affordable, and dependable energy production. So there's an increasing number of carbon capture plants in North America, and there's of course incentive for like tax credit programs for carbon capture projects at power plants and industrial facilities like ethanol, cement, steel, and industrial boilers. So at Gasmet, we have internationally some installations at industrial facilities like cement power, in power plants, yes, at cement facilities, and really anywhere you have flue gases and then concentrated components such as CO2 and other volatiles. So carbon capture for us is an important application because it includes a lot of these components that we could potentially measure with FTIR. Existing post-combustion carbon capture designs are diverse. The most common ones are based on membranes and others with absorbents such as amines. So these amine processes are well established, they're versatile, they're scalable, and they operate at atmospheric conditions. Some analytical challenges in them include that they have, of course, a lot of components there. So they go through oxidative, thermal, and atmospheric degradation. So they degrade into ammonia, which is the most common product. Then short chain amines like methylamine, ethylamine, acids and aldehydes, and nitrosamines as well. So the beauty of this all is that most of these components absorb infrared light, so we could potentially measure them with FTIR. So carbon capture plants are an optimal application for FTIR multi-gas monitoring. Here are some of the potential points of gas analysis. So we've got the overhead product of the absorber where you have exhaust gas with typical flue gases and pollutants is in some amine degradation products. The concentrations will really depend on the temperature of the column, the amine used, CO2 loading, and other components being present, such as SO2, NOx, H2S, and whatnot. These components are volatile, so they will tend to leave into the atmosphere, and they're also ecotoxic and carcinogenic, which is why they need to be monitored, right? Then another point of potential measurement is the concentrated CO2 stream at the top of the stripper column. Of course, CO2 is a very powerful infrared absorber, so we can definitely measure it up to 95 to 100% with the same instrument that we can measure CO2 at trace level conditions. There's also potential leakage points around the system as well, so we have manufactured instruments with multi-sampling units for channel switching. Sampling challenges, of course, include that it's a sticky and the mixture has sticky gases such as ammonia and some volatiles there as well. And analytical ones, of course, it's a complex gas mixture. When it comes to sampling difficulties, I was mentioning we're dealing with sticky gases, polar water-soluble components, so we've got ammonia in there, and the immediate challenge is how to transport them into the analyzer and ensure a representative reading of the sample. Well, we have a hot-wet extractive sampling system, so we keep the temperature of the gas stream above dew point. So typically it would be 120 to 180 degrees Celsius. So everything that's in gas phase will stay in gas phase, and we prevent or avoid condensation from happening. The advantage of a hot wet extractive system is that there's no need for preconditioning, dilution, or drying, and the gas sample remains, as I said before, in gas phase. So we will prevent these sticky gases from getting stuck into the inner surfaces of the equipment. When it comes to analysis, I was mentioning there's a lot of components, so there's potential interference between each of these gases and water vapor and CO2, which are powerful infrared absorbers. So we have to overcome that issue. With infrared, with FTIR particularly, we have each infrared gas, infrared absorbing gas has a particular fingerprint that we call the absorbance spectrum. So a mixture of components will have different peaks on it, right? So each peak's location determines potentially what gas we have there, and the higher the peak, the higher the concentration. So with an FTIR software, like the one that we use at Gasmet, we specify specific analytical areas for each component. And we also measure something called the residual. The residual is the difference between what we calculate to be the absorbance spectrum and the spectrum that we built based on the built-in references. So if there's a high residual, there is a potential for an extra component that is present. So what we do is every time we measure a gas, and we do so, or we give you a new reading every 60 seconds or every 20 seconds, we get a residual spectrum, and then we compare that against references for like 400 gases or 500 gases in our library to see if there is an unknown there that we can identify and add to your existing library. So after we do that, the residual value is decreased, and then that, of course, ensures a high quality result. So it gives a possibility for future-proof design, really, because you could even deploy the instrument for, let's say, to measure emissions from a thermal runaway event in a lithium-ion battery fire, and you're going to be potentially working from the same base library with new components. So these are just the internals of an FTIR system like ours. There is an interferometer where all the light is produced and modulated and applied onto a sampling cell. Then there's a detector at the end, and then we measure how much light was absorbed in the process. The screen with results looks like this. Everything comes from the absorbance spectrum, which is here. It's the raw data. And here's the residual result that I was mentioning before, which is a quality assurance statement on your results. There is a trend view with a concentration profile over time for every component in the system. As I was mentioning, this is a versatile system that allows for to identify new compounds and add them into your library. And it has safety features like service requests, concentration alarms, and automatic flushing, etc. Now let's talk about the different configurations for sampling. I was mentioning we deal with hot-wet extractive. We have semi-portable monitoring systems. In this case, our latest model is called the GT6000. It comprises the analysis system, which is the FTIR over here, connected to a heated line, connected to the portable sampling system that has a heated pump, and it draws the sample from let's say you're up in the stack or in a process line or in the laboratory via a heated probe and another sampling line in there. So everything, as I was saying, it's kept above 180 degrees Celsius, and it's a complete portable or semi-portable system that is operated from a Windows-based computer. then of course that is our portable version of what we call the SEM cabinet configuration, which is a continuous emissions monitoring system, and it's typical more in compliance monitoring projects. This is more of a process monitoring or process optimization application. So in such a system, you'll also have the FTIR, then you have a sampling system with a heated pump, you have umbilical heated lines as well and a heated probe. It's the very same analytical performance, just in a stationary format in a continuous measurement system where you get reading updates every 60 seconds. A typical carbon capture gas library would have post-combustion products, and we have a rich library with your common amines like monoethanol amine, AMP, piperazine, and other new components. Because again, every facility and like amines they tend to be proprietary, so every company will have their own. And at research and development level, there's always a new component, and as long as it absorbs infrared light, we could potentially add it to our library. Here's some examples of case studies. We've got a pilot plant at a power plant station in Poland where they chose a semi-portable hot-wet FTIR analyzer to measure flue gases that came from a desulfurization unit, and they deployed a scrubbing system based on amino-ethyl ethanolamine. So they were able to measure SO2, NO2, CS2, formaldehyde, and all these components, as well as amine decomposition products. So as with other carbon capture designs, they had three washing beds, which are packed beds with recycled water to absorb and condense volatiles to prevent their ultimate emission. So being able to measure amines over here at the top of the absorber column, they use the FTIR to evaluate the efficiency of the washing beds and make decisions on the spot. The same semi-portable system, it's deployed in research, lab, and field scale applications, such as studying degradation of common amines like MAE, as I was saying, AMP, piperazine, and of course always ammonia. And also the development of new formulas. Here's a couple examples. One of them at the University of Texas at Austin and University of Kentucky at the Appliance Center for Applied Energy Research. For research and development and lab applications, there's a great advantage in a portable system because it has a smaller footprint than other stationary products we see out in the market. It has a very easy setup with portable nitrogen bottle for calibration. You get quick results. It has the same analytical performance and results that you would get from a stationary configuration, and it allows for flexibility. You can change system parameters, flow rate, temperature, and see the results on the go, therefore saving in labor and laboratory costs. We have some installations using more of a continuous emissions monitoring or SEM type of cabinet. One of them here in the example, here's SEM installed at it's a cement facility by Lafarge, and the carbon capture plant was designed and built by Svante. They developed a membrane-based carbon capture system, and so they chose to have 3 sampling points at stacks with scrub gas that they wanted to dynamically control. So they chose to have a hot-wet sampling system because they wanted to prevent the necessity for water removal and or like drying or preconditioning. And also, of course, the FTIR, because even if they only were interested in flue gases and post-combustion products, they ended up having certain other volatiles in the mixture, and they were able to identify them and add them to their library. So that was a nice add-on. In this case, we had a system that we sold. It's also a SEM cabinet system that we sold to ProSelect in Vancouver, again in Canada. So they used CO2 that was removed from a biomass facility using carbon capture. So in this case, the sequestration and storage method of choice was a produced greenhouse. So they evaluated the effect of increased CO2 on the vegetable growth and production. The nice story about this is that the typical feed into such biomass facility is, or in this case, ProSelect was wood chips from the British Columbia area. And at some point, the feed changed to debris from a house fire, where there is, oriented strand board and plastic residues. And so the burning of those would give off, HF, HCN, HL. In having an FTIR system, we were able to identify them and add them to the library. So they were only buying this instrument to measure CO2 and maybe a couple other pollutant gases, and they got an entire system with more than 20 gases in their library. So you never know what you're paying for. In short, it's the economic life of a stationary system. It's up to 20 years. There's minimum consumables such as nitrogen for calibration, or like a background calibration every morning, span gas filters and whatnot. It's a system that only needs a visual inspection once a week. And you can add new components, as I was saying, even without any hardware changes. So it's very versatile that way and future-proof. The most important part of it is just the true multi-gas capability that FTIR has. It's a proven measurement technology and a flexible one at that. So again, future-proof. So thank you very much. And if you have any questions, let me know.
Question?
Yes?
Last night,
yes?
you mentioned the metro segment is great. Maybe the metro segment would be more
Nitrosamines, yes, depending, just a second. So yeah, we had some there. Yes, typically we can see, subparts per million. So we're looking at, the range-wise, we offer like 0 to 5 to 50 parts per million. Low detection typically would occur around like 0.5 parts per million to 1 part per million, which sometimes can be tough after the membrane. So yes, it can be just a couple parts per billion sometimes, but yeah, nitrosamines are one of those that are tricky sometimes, but not super low in terms of just maybe like a single part per billion, but we can get to like 100 parts per billion sometimes, yes.
Question?
Yeah.
So we heard this morning that sometimes for CCUS, the CO2 purity is, the pipeliners like to see 99.9% pure. Does FTIR have the ability to detect with that resolution, seeing down that purity?
So when it comes to that high, so if you have, we can do that. We've done 0 to like 100% CO2, which is typically the outlet of the strip or column, or the concentrated one. So typically I get requirements for like my clients go like 95-98% CO2. With the same instrument, it's possible, yes. The same instrument that, let's say, it's going to do ambient at, 600, 700 parts per million, although at such high concentrations, it's best to get a separate one with a shorter path length.
Okay.
Yes, but yeah, it's possible.
So the next question is,
yes.
So now that's part per million.
Yes.
Essentially, we're talking percent, so 10,000 parts per million.
Yeah,
so
exactly.
What about PFAS, where we need to detect down to part per trillion?
No,
That's not
we don't go
doable.
there.
Okay.
No, unfortunately, no, we're not. I don't know if there's more.
And then one other question. So, I'm involved in some projects that are natural landscape carbon storage and peat deposits using the Cabrera standard.
Yes.
Do you have an open path application?
No, but
there is. You shoot the beam over the
We've
wetland.
been asked about that because
Okay.
there's interest, but that's like at university level probably.
Okay.
I don't know if you've been asked about that. We have gotten so it's basically natural sequestration. So people
I didn't know. I
sometimes
wasn't sure.
You said they wouldn't work?
I said OpenPath in my experience doesn't work very well, just because there's so many variables you have to control.
Exactly. So I guess, so for peatlands, though, the most common design, it's on-site measurements. Like I was showing in the first slide, they want to do like very fine measurements at I can't move here.
Take a sample back to the lab.
That's the old method. I can't pull up. So back in the day, so what they did is they used like a PVC pipe. They install it on the ground, like let's say 48 hours to a week before you're going to do the measurements. Then you put a lid on it. Back in the day, I'm talking like 10 years ago, they would just take a sample, a manual sample, and then people grew old doing their PhDs, taking samples to the laboratory. Like my clients are like tired of this, so they had to take manual samples and send them to the laboratory. But it's a lot of human error associated. I mean, GC is pretty much a golden standard still, but we're not going to beat that. We just made it easier taking an instrument to a site, but not on a not in such open because if you're looking at OpenPath, what's the distance that they're looking after, right? If they're looking at high, very very large areas, probably they're looking at eddy flux columns, like eddy flux towers. They're able to measure very fine concentrations, like close to parts per trillion in the like tree canopy kind of sort of level, and overlap large surfaces. And here it's just I don't know what's going on with this computer.
The challenge that we face in application is that it's the one on scale. So the larger the scale, the more accurate the measurement in the sense that you're trying to come up with a carbon intensity per acre.
Exactly.
And so if you're taking a bunch of little lab samples, you're biasing the data, you're skewing the data to less CO2.
Mm-hmm.
And I'll just be blunt about it. The guys that are paying us to do this, they want to see the maximum CO2 that they can claim under the standard. So that's sort of where that comes from. So OpenPath would be a really economically attractive option.
Yeah, most of my clients are at research level, so they're trying to evaluate what's the effect, let's say, on the application of a certain fertilizer or a certain management practice, which is going to happen over a very tiny area, and what's the impact of that on, let's say, nitrous oxide emissions or methane. There is more interest now in larger surfaces, and there's a couple papers out there at certain universities, but I don't think there is an instrument doing that right now. I've seen one, like a Chinese manufacturer for ammonia, but not for the rest of components. And it may happen, at some point. I don't know what's going on with this computer, so it's just frozen.
I know.
And so I apologize.
Well, thank you. Appreciate talking. It is good that we mixed up some of these different topics.